Okay, good morning, everyone, and thank you for being with us. I really appreciate everybody making the time. I'm seeing some friendly names out there. Simon, all the way from Australia. Welcome again. Thanks for making it. Really appreciate it. From Gammatek's perspective, what we're trying to do is also look at doing more of these seminar, webinar presentations, which is informative and to give back, basically. And for those of you who don't know me, my name is Marco Gonzalez. I'm Gammatek's sales executive. And today we are proud to be able to do an introduction on acoustic emission applications. And this will be presented by Malcolm Howes from SSA Acoustics and Specialized Inspection. Just some house notes. If you've got questions, you'll notice you've got a chat box that you can actually put your questions there, or you wait until the end of the session for the question and answer session. So without further ado, I think, Malcolm, the show is yours.
Thank you, Marco. Thanks everybody for joining today. Today will just be an hour-long presentation on an introduction to acoustic emission. So I will go over some of the basics of acoustic emission, head into the equipment, and then go on to a few applications, a few good examples. Now, if there are any questions, please use the chat. I'll ask that the administrator just mutes everybody so we don't get background noise during the presentation. But please, if there's something very important, just send a few messages on the chat and we can halt and move forward. Otherwise, all questions to the end. Okay, so let's start at the very beginning, basically. And what is acoustic emission? Now, the formal definition is acoustic emission refers to the generation of transient elastic waves in a material, okay? Just means it's a sound wave in a material. Now, these sound waves have to have a source. And this is where acoustic emission comes in. I'll abbreviate this to AE during the course of this presentation. And we use acoustic emission to obtain useful information from these sound waves. So very much like ultrasonic testing, but there are a few differences. Now, if we jump into the history of acoustic emission, now it started way back in 6,500 BC when potters used to listen for cracks in their kilns for pottery. It then progressed slowly, very slowly, where metal workers used to listen to the cracks propagating the cry of tin between 6,500 and 3,700 BC, and not much change until the 19th century. Here we have an example of what stress relief in acoustic sound generated sounds like. And you have multiple metals that do this. So tin is a noteworthy one here, iron, cadmium, and zinc. So the early metal workers used this quite extensively. And that's sort of the roots of acoustic emission. Modern acoustic emission, however, only started around the 1950s after the German Joseph Kaiser started studying this response in materials. And his main contribution was finding that materials retained a memory of previously applied stresses. So if, for example, you took a plastic ruler and you bent it, you'd hear the cracks. That's acoustic emission. If you bend it to the same point again, you most likely won't hear those same cracks. Now, we've gone on and said, oh, this produces acoustic emission, this and that. Now, anything that generates sound wave in a material, that can be considered acoustic emission, can be detected by our sensors. But what are we interested in the oil and gas industry? Well, obviously, crack propagation is first and foremost. So acoustic emission, the bonds breaking, surface creation, reduction of energy, that energy is transmitted to sound and travels through the material. Another obvious note is impact of particles. If a particle impacts a material, it produces a sound wave. Chemical processes. Now, these are much softer than the others, but more difficult to detect. But chemical phase changes and reactions like corrosion can produce acoustic emission. Friction and fretting. Obviously, if you rub your hands together, you hear a sound, acoustic emission. And lastly, turbulent flow. So yeah, the flow of a fluid won't necessarily produce acoustic emission, but as soon as there's sort of turbulence, unknown sort of chaotic movement, turbulent flow, you will get acoustic emission there as well. Moving on to how we detect it. So we have a simple sensor, piezoelectric crystal, where acoustic emission is emitted from a source. For example, any one of the previous ones, for example, a crack, heads to the acoustic emission sensor, it then just gets digitized, sampled, and sent into the PC. And we get a waveform, something similar to the right, on the right there. Now, the raw waveform looks something like this, and this is just, it looks like a normal RF audio signal. Now, back in the day when they were first developing this technique, the gents would actually print out these waveforms, raw waveforms on paper, take a ruler, and then draw a line just above the background noise level, and then have a look at all these events. Now, this is extremely time consuming. If you're looking at a corrosion test, for example, you have 180,000 of these hits, as we call them, or events, in an hour-long period. Luckily, with the introduction of computing, we can detect these points or events. So we set a threshold, and every time the signal crosses that, we have a look at that, and we can obtain some information. This is the hit-based architecture, which is used extensively in most forms of acoustic emission, except maybe for leak detection. Now let's get on to what these hits or these signals, events look like. You get different types. Let's look at burst signal, for example. This could be a crack or impact particle. It's just a short, sharp, loud sound. It doesn't stay active for very long. Or you can get continuous signal, which is drawn out. This could be friction or turbulent flow, something that takes a bit longer, basically. You get many, many other forms of signals that you can use to obtain information of the source of these signals. Now, how does acoustic emission compare to other NDT methods? And this is a very big point, because it's not very conventional in the form that we don't put any energy into the inspection. We just listen. So think of it as a doctor's stethoscope here, where we're simply listening to something happening, like a crack. So acoustic emission will only detect a crack if it's growing. If the crack is there and is laying dormant, you're not stressing it, you won't detect anything. Whereas other NDT methods, you'll actually see the geometric flaw. Another major difference between acoustic emission and other forms of NDT is it's best suited for monitoring an entire structure, a global monitoring technique. So if you put sensors on a part of a structure that is acoustically coupled to the rest, you will detect, obviously, if it's loud enough, a source being emitted. Whereas most other techniques are local scans. So you would take a UT probe and physically have to move it over every millimeter of a structure to scan it with UT. Whereas acoustic emission, you put sensors at set termed intervals and you listen. As I mentioned before, Kaiser introduced the idea that every time you load the structure, it will emit to a certain point. It will crack, and if you load to a point below that stress level, you won't see much more. Now, that poses a few problems for repeatability of acoustic emission, because once you've stressed the structure, you've stressed it. There are cases where the structure sort of heals over time, and you can then stress it to that same point, where in other forms of NDT, you can easily repeat this. Now, acoustic emission, you can repeat the same test on different assets and get the same result, and that's how you get your repeatability. Now, the response we receive is directly from the source. So we can infer quite a bit of information because it's coming from the source, whereas other NDT methods, the response comes from the shape and size and orientation of the floor. Now, bearing these differences in mind, acoustic emission has various advantages. So we can rapidly detect and locate defects in large areas. So for example, if you take a storage sphere, if we're able to pressurize that with a couple of sensors on, there's about 12 sensors on this particular sphere, we can test the entire structure in a couple of days compared to a couple of weeks if we were scanning it with UT. Another advantage is we only detect active defects or growing defects. So if a crack is laying dormant and not propagating at that pressure, we won't see it, which is great for older assets. That's particularly here in South Africa, we have a number of assets from the 1960s and 70s with a lot of these older manufacturing defects that aren't growing in service. It's also very well suited for in-service inspections because the sensors just need to be attached to a part of the structure that's acoustically coupled. You can also use these in-service inspections to fit into a continuous monitoring or an RBI, risk-based inspection program to get credits and push out our inspection dates. Now, the major benefit of Acoustic Emission here is actually cost saving. If you take, let's look at the previous points, rapid inspection of entire area. So if you're paying an Acoustic Emission team for 3 days to inspect your entire structure, compared to a couple of weeks scanning with UT, saving time, saving money there. You will also only detect defects that are growing, so only defects you need to be worried about. Then you can focus your maintenance and repair budgets accordingly. Plugging the information into in-service inspection, you can do in-service inspections and move out your inspection dates if required, based on good data, and once again, saving money. So saving money is a massive factor on Acoustic Emission because it is so well suited for in-service inspections. Now, limitations. Once again, it only detects active or growing defects. Now, it's an advantage and a limitation depending on what your application, what your damage mechanism is. So this is a limitation that clients need to be aware of, and any professional in the industry. Acoustic Emission only admits on, the emissions will depend on the stress history. So for example, if you are attempting to test a structure that's recently hit its PRV valve, so it's gone over, burst a PRV valve, bursting disc or two, you will need to stress that structure over the previous pressure to actually perform a valid inspection, which isn't really a problem in industry because there's multiple levels, stages of PRV valves, but it's something to bear in mind. We also cannot characterize or size your defects. So the data we receive is very much, you should go and look in this area, there is a defect over here. So we detect and locate. We don't really characterize and size. That is up to the follow-up NDT accordingly. And we head on to noise sensitivity now. Acoustic Emission is extremely sensitive. Almost everything makes a noise. We can detect the movement of a nucleus, for example. Now, the main limiting factor in industry is actually the noise. In the lab, we can do great things. In field, we obviously are a bit limited. So here, if Acoustic Emission is so sensitive, why can't we it can detect every crack and corrosion spill, why don't we use it for everything? Main answer there is noise. If we compare the loudness of a corrosion, few bonds breaking during the oxidization process, and that transmitting a sound, compare that to just a droplet of rain falling on the roof. That's a massive difference in energy. Now, this can be extrapolated to condensation, pumps running, people walking on the tanks, weed whackers flinging up debris, birds fighting on the tank roof. Yes, we've had that. Or lizards running and attacking sensors. We've seen it all. So, for example, if we're monitoring some corrosion, so here's a graph where we have sort of the intensity or strength on the vertical axis, and horizontal is time. Corrosion activity generally comes in as a bunch of bonds breaking, a little tick as it goes on. In this particular test, everything was fine. We have a bit of noise there. We're monitoring corrosion activity, and all of a sudden it starts raining. And that's what the data looks like. Now, that is extremely loud to our sense. That you could say is a thunderstorm. No, that was just a drizzle. And that is how sensitive some applications are. Now, with noise being such a limiting factor, we obviously have to develop ways of dealing with the noise. So there are a few workarounds. Obviously, the first and the go-to option, the best option, is remove the source or perform the test when the noise isn't present. So in our raining example, just perform the test when it's not raining. Switch off connecting pumps. So another important factor here, the noise I'm talking about is acoustic noise. So that's rubbing on the actual tank or the vessel itself compared to just standing there shouting at the sensor. Airborne noise, it doesn't really transmit into the materials very well. So we're pretty much immune to that. Alternatively, we can adjust the frequency. So acoustic emission, we generally operate in the 10 to 400 kilohertz range, so slightly lower than ultrasonics, but still higher than the human ear. And we can apply certain filters. So we can choose the sensors correctly or adjust analog filters to be more sensitive to corrosion, which is on the lower end of the spectrum, which is also where the noise normally sits, or adjust the frequency. So we only detect higher frequency emissions, which would be cracks in that, which are very loud. So depending on the type of test, we can effectively eliminate most of the noise. We've performed many tests in the oil refineries where it's very loud, many pumps running, and we just need to be careful, and we can deal with that. Another option is to raise the threshold. So as I said, the gentleman back in the day drawing a line with a ruler on a piece of paper, that is the threshold. So basically, at what level do we actually look at the signal, and what is just background noise, electrical noise, etc. So the first example here is where we have our threshold set so low, it's actually in the background noise level. And that's just going to saturate the system. You're not going to get very much information out of that. If we move the threshold a bit up or higher, we decrease sensitivity a bit, but we are then able to focus on the louder points in the signal and the more interesting events, because generally looking for cracks or big leaks, etc. However, if we move it too high, we're not going to detect anything. So just a note here, if we do raise a threshold, we inherently reduce sensitivity. So to counteract that in the field, we would normally move our sensor array closer together so that we can then have the same sensitivity and pick up the same small cracks, but they won't attenuate out. And then the final option is to post-filter. Now, this is not recommended. Generally, when you do post-filtering, you're removing sources from a certain located area that you know should be noise, and that's based on an assumption that should be noise, or bits of time. So there is the chance that you're filtering out real, genuine acoustic emission data. So this is the last resort, basically. Now we go on to the location. Now there are various forms of location in acoustic emission, and generally we put multiple sensors on an asset, and then we can go through different degrees of sensitivities. The first is zonal, and this works on the premise that the first sensor to pick up a sound is the closest, which makes sense. So your source position might look something like that, where your actual PC output would just be general area. And this was very effective back in the day, and most of our modern location techniques is just built on this. The second is planar. So this is the traditional triangulation, same idea as GPS coordinates or GPS positioning, where if you were to have a sensor array, here we have a sensor array with some blue dots there representing the channels, and then you have the red circles where you simulate position. Now the PC output would calculate the difference in time of arrival of these waves, and you would get a plot something like that. Now notice that there is a bit of error there, and that's because the sound waves do not travel in the perfect straight line. They do bounce around a bit. The timing is a little bit off, etc. So the nice thing with acoustic emission is it's a statistics game. Because you're dealing with so many emissions in general, hundreds of thousands sometimes, you get a good statistical distribution of its location, and you can pinpoint that way. Now we move on to 3D location. Obviously, we just extrapolate, put more sensors on the surface, and we can do surface location on the entire structure, or even true 3D where you need 4 sensors and you can pick out the exact X, Y, and Z coordinates. All right, now let's move on to attenuation. So energy isn't finite, isn't infinite. It does, the signals do reduce the energy the further away you get. So if you're shouting at someone, the further away, the softer it appears. Same thing with acoustic emission. Now we have to be very careful with attenuation because we are just listening. So we need to make sure that if we want to detect every defect on that structure, we need to make sure that we're covering the whole structure in our sensors so that any one point is accounted for. So our attenuation and noise level determines how many sensors we place on a structure. So here's an example of an attenuation curve where we have the intensity or decibels on the vertical axis and distance on the horizontal. And basically, we can effectively say we can effectively detect a source X amount of meters away, depending on our threshold and how well the structure transmits the sound. We can then plot that on a graph and get a sort of a probability of detection or attenuation graph on a specific array. Now, let's head on to the more interesting side. Here we have acoustic emission applications. Now we're getting into this a bit late, so I'm going to just brush through a few, but in the petrochem industry, we are looking at crack, corrosion, and leak detection and location. Those are the main problems we are solving with acoustic emission. However, we can detect anything that produces acoustic emission. So we have a lot of obscure applications. Here's a quite extensive list, but this is by no means all. Some of my favorites here are bridge monitoring, continuously in service for failure. Formula One cars use it in their composite research, and rockfall early detection, etc. Now, we will be looking at 3 particular applications, namely crack detection on pressure vessels and storage tanks, corrosion monitoring on vessels, and then through valve leak detection. So if we start off with the first application, which is the crack detection, it detects and locates active defects. So this could be hydrogen blisters going stepwise cracking, normal cracking, SEC, whatever it is. We inspect the 100% of the structure by placing our sensors accordingly, and we can detect relatively large inspect relatively large structures in a short amount of time, 3 days for a medium-sized vessel, for example, and compare that to scanning with automated UT, which could take up to 4, 5, 6 weeks. And this can be done in service or inspected in service. So on a vessel, we would pressurize with the product that would be in service, and whilst we're pressurizing, we would monitor for cracking. And it's best used with an RBI program. Now, the data you get looks a little something like the images on the right, with your few graphs, location, and then an overall summary. So there are various methods for evaluating acoustic emission data. In this case, we use the MONPAC grading system developed by Mistras, where it ranges from no further action required to have a look at it visually, follow-up NDT, or immediate follow-up NDT to confirm. It then is able to give you a recommendation on a reinspection period from immediately to 5 years, basically. And this is based on an empirical database of thousands of assets which they've inspected. So how does this method look like when we actually implement it? So first up, we need to obtain the asset history and information. And this is very important because, as we said previously, each loading is unique and we need to stress the asset to above what it's previously seen. So we'd go in, attach sensors via magnets, usually, either via rope access or scaffolding. We then pressurize, monitor the vessel, and interpret the results. Now, here we have a case study of a composite vessel being pressurized. You have the vessel in the center here, undergoing pressurization via this pipe. you have a little preamplifier here for one sensor that's attached over there. And you'll find out presently why they've only used one sensor here. On the graph, you have the pressure going up, and these dots over here represent acoustic emission. So the higher it is, the more energy, and the more dots, the larger number. And we have time on this axis. So as we're pressurizing this composite material, should it begin to fail, we should expect to see some emissions starting over there. And then as the fibers in the composite material break, you should have a reduction because their load then falls to the better fibers. So you have a reduction in noise and it ramps up again. And you get this oscillation type, and that's very unique and archetypical of composite materials. So here we can see immediately, well, hang on, there's some failure happening over here. There's some acoustic emission, and at this point, as soon as we see this oscillation, the acoustic emission technician or field engineer on site would immediately tell the pressurization team, well, hang on, you need to slow down, stop, let's investigate further. And about at this time, we would be screaming on the radios to tell the gents to stop pressurization as we just gap it basically away. You can see there's no visual cues on the vessel yet, but the acoustic emission is, you can definitely tell that, hang on, something is going on there. There's some cracking, there's permanent damage happening to the structure. We should have one final rally here. So you can see that the average of the emissions is decreasing. However, you do get these spikes, and that's as a bundle of fibers snaps, load falls to the rest, etc. And then finally, we have a complete and utter failure. And that $700 sensor is blown to smithereens as well. So that's the first type of cracking case study. If we look at the second case study I have in store, we have a 30-meter diameter cryogenic storage tank, very large surface area. We attached 64 sensors to it, and we filled with product to simulate the stress. And we're looking specifically here for cracking, SCC, etc. Now that's what it looks like inside. It is insulated. So we would go in, attach the sensors directly to the tank wall and cover up the insulation and then load up the tank. The results that we received looks something like this, where we had 2 clusters on the tank, which we can't tell you what they are. We can tell you there's AE activity there. It looked kind of crack-like. You should probably investigate visually and or NDT. The follow-up TOF data actually revealed various laminations in this vessel. So if you have a look at this vessel, we inspected in about 6 days total. And you have 2,000 meters squared of surface area to scan. That was done in 6 days. And we found laminations 10 to 30 millimeters long. So that is equivalent of finding a blade of grass on a standard football field. So it's very quick, very effective for detecting active defects. Now, a thing to note here, there were other cracks in this vessel that we were monitoring more closely, and those were latent, so they didn't propagate. AE data didn't show it. Move on to the second application, which is corrosion monitoring. This can be performed in service. It provides active corrosion data, and we can detect very large tanks in a very short time period, sort of up to 110 meter diameter tanks. Underground storage tanks we can also inspect using this method. It does not provide the remaining wall thickness though. We are able to provide you acoustic emission data and recommendations based on a database of thousands of tests, but we won't give you the wall thickness. There are methods of detecting and quantifying corrosion rates in the lab, but in field, it simply does not work at this point. And this is very effective when used with an RBI program or the EMEO 159, which is a bit more progressive than the 653, has provisions for acoustic emission. Now, the data that you receive looks something like this, where you can easily see on the left here, we have less dots, so therefore less acoustic emission data, as simple as that. Whereas on the right here, we have a higher activity tank. In this case, this tank was corroding on the annular quite significantly. So this is the data we give you, along with a recommendation of, okay, retest in 4 to 5 years, or schedule for reinspection, or an internal inspection in 6 months. Moving on to the method, we would obtain the history on the asset once again. We would then attach sensors to the tank shell. So even though we're looking at the tank floor in this case, because the probability, the generic failure factor of tank floors is 10 times higher than the rest of the tank, we attach the sensors to the shell and monitor the floor. And this is due to the fact that the corrosion emissions travel from the floor through the product and in and hit the sensor over there. So we detach the sensors, check that they're functioning, monitor the vessel, and interpret results once again. Now, the typical data you'd see would look something like this. We've already seen that. And when comparing to the MFL data, actual physical thickness, you can see that there's a strong correlation between the location and intensity. So that section over there would correlate with that increased activity. And there are thousands and thousands upon these tests performed. And based on that, we can then make the recommendation for the reinspection date. Final, second last case study is corrosion under insulation on a pressure vessel. So here we have a vessel insulated, which sensors were then attached to and monitored during pressurization. Now, instead of finding cracks, in this case, we actually found some concentrated data right at the top of the vessel. When you zoomed in, it's sort of as a horizontal linear form. And this actually correlated quite nicely to the wind girders and stiffener rings, corrosion, the insulation supports rather, where water had ingress and you got corrosion under insulation. So on a large structure like that, test a couple of days and we can find your corrosion or cracks. Final application is leak detection. So this can be detected in service, able to detect leaks down to 1 liters per minute. And it's a quick inspection, 5 minutes per valve, and you can do it in service. Test method is very similar, except that we only use one sensor. We acoustically couple the sensor to the valve, and we basically just check for turbulent flow on the valve, and we can actually quantify the noise. And this is based on the principle, should the valve not be seating correctly? Let me just get my pointer out here. Should the valve not be seating correctly, you get turbulent flow, produces a noise, sensor then picks it up. The more product flowing through, the more turbulent flow, and generally the higher pressure, you would then pick up more AE data. So you can quantify it as well. Final case study here for leak detection. Just on a pipeline, we can detect through wall leaks out into atmosphere or through valve. In this case, it was through valve. A couple of sensors were attached to the pipeline and monitored accordingly. Now they had a flow meter on the leaking valve, which then could be correlated with the acoustic emission data. So here we have a few examples of the data where the normal 7 bar not leaking, and that's when we have a leak at 7 bar. And as you go up in pressure, more product, higher signal, more energy being transferred. And that's the basics of how leak detection work. I'm not going to go too much detail there. And that actually brings us, with 1 minute to spare, to the end of the presentation. I see there are a number of questions in the chat which I'll address, but thank you very much for attending. I hope this has been informative. It is a very basic introduction. There's many aspects of acoustic emission that I've left out here, many applications, but I am available for any questions. My email address is there, or you can forward them on to Gamatech should you require. A recording of this presentation will also be available to all those that attended. Are there any questions? Could we just unmute the audience here, please? Marco?
Hey, Malcolm.
All right. I see the questions in the chat have already been answered. Okay, here. What is the maximum shell temperature that the sensors can be attached to? So these are very similar to ultrasonic sensors. And so generally there is a limit of about, call it 100 degrees. However, high temperature sensors can be applied and attached, and these go up to about 140, 150 degrees Celsius. Now here, we can work around this by acoustically coupling the sensors via just a long rod with a sensor on the end, which is then welded to the structure. Now this standoff reduces the temperature to a manageable rate, but it still leaves acoustic coupling. We do reduce sensitivity, but you are able to do it. So this is quite often used in pipelines, high temperature pipelines that may have a crack in that has been clamped. We would then weld a few of these waveguides on, attach the sensors, and monitor the crack or area of repair for any further crack propagation during startup especially, and in service. So
Malcolm, sorry, just one point maybe before people do possibly leave or need to go. If anyone has any suggestions on other presentations to do in the future, please feel free to drop them here or just email us. We'll happily look at it and see if there are either ourselves or other experts in the field that would be interested in hosting seminars with us. Thanks.
All right. We have a question here about, is acoustic emission limited to regular geometry? So no, definitely not. We actually, anything that's acoustically coupled, location obviously becomes a bit difficult. But here we have quite a few examples. Let me just get to my application slide here. So we can even, the acoustic emission is used for wood drying. So you could attach sensors to trees and have a look at how well they're drying. You could attach to very strange geometries. So if you have a particularly strange setup of a pipeline, so various loops, etc., and you don't particularly need exact, precise to the millimeter location, you just want a general location, you would then attach sensors to the entire line, maybe a bit more to more complex geometry, and you can get a general area which then you can focus with your follow-up NDT applications on. So even vessels, so if you have a pressure vessel that is jacketed and you're looking, say it's got welded half pipes on the outside, you could actually fill those half pipes with water or even leave them unfilled, attach sensors to the outside and pressurize the vessel, and you'll be looking at the internal wall as well because that is being stressed, and you'll be able to get an estimate location on that. I hope that answers that question. Is there anything else? Are there any other questions? Okay.
Can you hear me?
Yes, I can. Go ahead.
Ababakar, so it's from Bureau Veritas in Angola. Several times you mentioned the load history, and you say that so the equipment has to be stressed above its previous load. Can you explain it a bit better, please?
All right. So if we go back to the plastic ruler example, if you take a plastic ruler and you just simply bend it, you will hear the cracking. You can hear it. Now you release the pressure or the load and you bend it once again. If you bend it at the same point, you probably won't hear the cracking audibly again. However, if you go past that point, you will hear the cracking. Same thing in structures, where if your vessel has seen a certain load and pressure in service, if you apply the same load or slightly below, you most probably won't hear the acoustic emission. But if you go slightly higher, in practice we go 5 to 10% higher than previous maximum, we are able to detect and locate the defects there.
Okay, so it makes a difference between pressure equipment and storage tanks.
Yes, so here we're looking at, with pressure equipment, we're looking for the load. We need to apply load for acoustic emission. Storage tanks, we can do the same by filling if we're looking for cracks, or alternatively, if we are looking at corrosion on the floor, the stress of the chemical stress is already there. So we don't need to apply anything. The corrosion will will continuously happen, and we can then detect and locate it accordingly.
Okay, yeah, thank you.
Okay, perfect. Okay, here we have a question for corrosion under insulation on piping. Acoustic emission is quite effective for corrosion under insulation on piping. We would just need to cut out holes in the insulation, attach the sensors directly to the piping, and then monitor. Now, here there are various limitations. So generally, you will need to attach the sensors about, let's call it about 5 to 10 meters apart. So it might drive up costs because of the number of sensors that you attach to your piping. The other issue here is if you're monitoring in service, if you're looking for corrosion or even SCC in some cases, and you have a very high pressure line with a lot of fluid flow, and the fluid, say, has debris in it as well, that noise level might raise the acoustic emissions signal so much in the amplitude that the cracking and corrosion is hidden in the rest of the data. So there is that noise factor into it. But if you have a pipeline that is out of service, we could attach sensors to it and detect the corrosion and insulation and locate it, yes. In industry, though, it's not really used unless it's monitoring longer term, basically. All right, there's quite a few questions here. Let me just get the first one I saw is, how does sludge affect acoustic emission in storage tanks? That's a very good one. If there is a bit of sludge in a tank, that's not an issue. It will throw out our location a little bit and decrease our sensitivity. But in general, we acquire 10 decibels below what we evaluate. So if you have sludge inside your tanks, as long as it's not too high, we can still detect it. So if the sludge is too high, our sensors are moving further and further away from the floor. Therefore, we might attenuate out the signal, and there will be a cutoff to where we place the sensors, because we can't put the sensors directly at the sludge level, basically. So at the point that it becomes, at the point that we may lose data and not detect it because it's attenuating out to the sludge, we will basically call off the test and say, no, let's rather not use acoustic emission for this. Rather take the tank out of service, desludge, or perhaps sludge profiling to evaluate first, then desludge and go from there. Okay, what parameter has been used in terms of number of sensors? So when determining the number of sensors, it is basically all up to the background noise level, which we can say, in this example here, acquisition threshold. So everything below 55 on this graph, we can say that's noise. There's pumps running, acquisition, electrical noise, etc. And if you note, if we move this acquisition threshold up, because this is the curve, so this is a let me just start there first. This is a simulated emission, which we do using a mechanical pencil, about a 0.5 millimeter lead 2H, and you break it on the surface of the vessel, and you move further away from the sensors, and that's how we get the acoustic attenuation. And you get a curve, something similar to this. So as soon as your noise level increases, you'll notice that the distance that you would effectively inspect would decrease. And that's how we would determine the number of sensors. So quite often, based on experience and history, we know, oh, we should get about 5 meter radius around each sensor. And then obviously we want multiple sensors to detect it. So we basically use a 50% redundancy factor in sensor spacing. So we move them a bit closer to each other. And when we go to approach a vessel, initially we would say, okay, let's attach them. Let's do an attenuation study, confirm that our sensor arrangement that we have planned is correct. And if it is, we move forward with the test. So acoustic emission can be used for in-service tanks with product inside. You actually have to have the product inside to evaluate the corrosion. So you have to have the product causing the corrosion reaction to pick up the signals to detect it. So the methodology here would be to attach the sensors whilst the product is inside the tank, and then listen for, we need an hour's worth of data, and then grade that accordingly. Now, we can detect how active or how much corrosion is coming from the floor, but we won't be able to tell you how thin it is. The acoustic emission will also detect all the corrosion activity from the floor. So whether it's top side or bottom side, we will detect it. We won't be able to tell you whether it is top side or bottom side, but we will detect it. All right. Is there a minimal detectable limit? Yes. The limit in our decibel scale, we only go to 100. In general, you have a limit with electronics at about 25-30 decibels. That's all the electronic noise that you can't get rid of. And that's come down from about 30-35 before better boards were made, as it were. Now, minimum detectable limit, I don't know if you're referring to that or the actual defect. Basically, if you have, for example, the SCC, where it's a very small crack or even micro cracking, we will detect it if our sensors are close enough and it hasn't attenuated out. So we could attach hundreds of sensors on an asset and monitor accordingly, but we need to then look at the cost to benefit ratio here. What is cost effective for the client to evaluate the asset? And in general, we can easily find a very small cracks, 2, 3, 5 millimeters in an asset if it's growing in service. Okay, so here we have a good question regarding cracks that have been arrested. So this is if the crack has been arrested and it is not growing when we stress it, we won't detect it. So it is quite often used to actually evaluate repairs. So if you were just to do a normal welding repair, and you do, even if you just load it the first time, you'll de-stress, you'll get settling, etc. So what we do is, if you have a welding repair in a vessel, we stress it, monitor it, you get a whole bunch of emissions from it. We then unload the vessel and take it up to just below the previous loading, and you should see almost no emissions from that vessel then, because all the stress has been relieved in that vessel, and we can then evaluate if there's continued damage even after stress relief then. So for the bridges, here we have, is it only applicable to long-term monitoring? It is best used with long-term monitoring. In general, the bridges that are monitored are the ones that we're concerned about because the number of people that need to use it each day. So generally, you'd attach hundreds of sensors on these bridges usually and monitor it under traffic load. And the way the location mapping works is more zonal than anything else. Because of complex structures, you don't know exactly where the sound path will go. So you can't get your timing difference correct because you don't know the exact distance. So you detach many sensors, do zonal location on it. Alternatively, in theory, you could be able to load a bridge up with, say, water weights. So you pack water weights on there, load it slowly with water, and then you can stress accordingly according to the procedures and detect it. But it's most effectively used for long-term monitoring. We have how accurate is AE relative to UT. It's a bit difficult to compare directly. Acoustic emission can detect the movement of a nucleus in an atom. So it is extremely accurate. However, you have noise that's limited accordingly. So if you're comparing it to the minimum size crack found in a material, UT phased array in that would detect all cracks, where Acoustic Emission would detect the active ones. And depending on how far the sensor or how dense your sensor array is, how many sensors we have on there, we can get just the same amount of sensitivity as UT. I mean, if you have a crack happening directly under a sensor or just an inch away, you definitely detect it, no matter how small it is. We have a question here for different sensor types for vessel thicknesses. In general, no. And this is because we're not inputting signals. So it's not like UT where you can need a lower frequency sensor to get more penetration. Acoustic emission, we're more worried about what the source or the damage mechanism that we're looking for, what frequency range that falls in. So if you have a very thick vessel, we might move the, or say your areas of interest are further away, we might use just more sensors in a denser array rather than changing the type of sensor. All right, I think that is the last of the questions in the chat. Are there any final questions that you'd like answered?
Malcolm, I don't know if it's been said, but I'm sure we can get these questions in a Q&A summary as part of what we can distribute back. So
yeah,
that
perfect.
Questions can be listed as Q&A, and detailed information with referencing to where more information about it can be put back to everyone.
Yeah, perfect. Sorry, I just get very excited when there are questions. I sort of revert back to my lecturing days, as it were. All right, everybody, thank you very much for attending and for the questions. If there is anything further, please contact myself or Marco or the Gamatech team, and we'll be in touch. Have a good day.
Thanks, guys. Malcolm, very well presented. Well done.